Welcome everyone to PIRL 20. Thank you all for coming. Hopefully, as Jim said, we will be back on the beach again soon. But today we have Doug Hood here. He is from Oracle, and he is one of the evangelists there for Oracle x10. And he is going to talk about the reality of using Intel Optane persistent memory with an SQL in-memory database. Take it away, Doug.
Thank you, Steve. Good morning, afternoon, everybody. My name's Doug. I'm going to be talking about our experiences for using Intel Optane persistent memory for our in-memory database. So I'm a developer.
May I interject for just a moment? Doug, this is Scott from the control room. Do you have video enabled?
No, and I don't want to.
Okay, so for those on the audience, you'll see his slides, but you'll only be able to hear him. Thank you, Doug.
Yeah.
Go ahead. I apologize for interrupting.
No problem. Developer and product manager at Oracle for database development, which is a fancy way of saying I create bugs in C and I sometimes fix them. So we're going to be talking about our experiences with using both app direct mode and memory mode for our in-memory database. It's about half the talk. And the other half is looking at some very specific benchmarks that I was interested in, and based on, depending on how fast I go, should take about 45 minutes. So hopefully there's lots of time at the end for the questions. So one thing I just want to be upfront about, I normally have it as a later slide, but I think it's important. If you don't know what's going on under the covers with persistent memory, it's kind of like magic, and I don't like magic. So I'm a firm believer in looking under the hood, figuring out what's happening, specifically looking at the CPU counters. So you can do that yourself with perf event open, or you can use tools like I Know What I'm Doing, or the process monitor in Grafana, to see exactly how many memory accesses are occurring. So there's what you think's happening and what's actually happening. So we're using the latest and greatest version of the x10 in-memory database, and we're going to be doing some benchmarks. It just happens to be a C program. This source code's available on GitHub, so there's no hidden surprises. So this is a blatant Intel marketing slide. The reasons I'm showing it, apart from being pretty, since the first computers, there's always a memory hierarchy. Top is expensive, and as you go down the hierarchy, cheaper. So that's point one. Point two, Intel is absolutely dominating the space. So that's just a nod to Intel. I'm a fan of this technology. Now, as I work for database development, I'm going to talk about persistent memory through the lens of databases. So for about the last 40 years, the model for whoever's database has been you persist data on files on the file system. So, be it a spinning disk, or more recently with solid state disks or NVMe, you have persistence on disk and you load the data into memory as needed via techniques basically called buffer cache management. The point is you can have petabytes or zottabytes of storage on disk and load the data as needed into mere gigabytes in memory. So that's a pretty simple model. It's worked for 40 years. Persistent memory has new technologies, which creates new opportunities. And there's different ways that you can exploit those opportunities. One of the ways of doing that is using persistent memory as part of your storage hierarchy. And that's exactly what Oracle did with Oracle Exadata. So there was a talk last year about using persistent memory with Oracle Exadata. And Gia is also going to talk more about that on the 30th of October. So I'm not going to talk about that. That's one approach. Another approach is to use persistent memory out of about that. I'll talk about another approach, which is don't use the buffer cache at all. What I mean by that is I keep all of the data memory in the memory database. Persist the data to the file system, but you can use persistent memory to extend the DRAM. So this is, so if we look at the details of that, all of the data in your database in memory, it's going to be really fast, but there's a trade-off. If you have terabytes of data, that means you have to have terabytes of memory. And as we all know, DRAM is expensive. With an in-memory database, you don't have to have fast persistence and loading of your data, but it's highly desirable. So these are some of the challenges of using in-memory databases. So Intel Optane persistent memory provides technologies that mean it's got large capacity, it's more cost effective. Do you want to persist to the memory itself or to other storage devices? So what it's getting you is choices, but it's not that simple. You know, as Grady Booch famously said, a fool with a tool is still a fool. So what I'm saying is, persistent memory is very good, but it's not magic. Because I talk to some people and they literally think it's magic. I'm saying, yes, but. So you still have to make the hard design choices. And you know, the prior hour, we had some very smart people talking about some of those hard choices. The other thing is, it's got higher capacity, but that capacity today is still finite. 512 gig is the current limit. You know, maybe in the future, that'll be bigger. It's also cost effective, it's not a free. So the point is, it's really good, but an engineer, as an architect, you still need to make the hard decisions. So I'm going to be talking about using memory, specifically Optane. 2008, for Optane persistent memory was publicly available as a beta. Back when it was alpha technology, Intel was kind enough to provide us some system to test some stuff out. So we had a very hard deadline of less than 2 months to get some technology, figure out how to use it, and do something with it. So I'm going to be talking about that experience, and also what we've been doing more recently using persistent memory in memory mode, which is commercially available now as a certified configuration for the x10 memory database. So as you all know, Optane persistent memory has, I'd say 2 modes. It's really got 3 modes. With that direct mode, you have persistence. You have to explicitly design and code for that. In memory mode, you don't have persistence, but it just works. So more specifically, with app direct mode, you get to make the choice of, for your data structures, your objects, if it's transient, should I be putting it in DRAM? Or if I want to keep it, I have the choice of putting it in persistent memory. So you have power, but you have to make hard decisions. In memory mode, you don't get to make those choices. You just use memory. So it's simple, but you don't get to choose whether the data is in DRAM or persistent memory. So it's simple, but you have less choice, less control. That's sort of in a nutshell. So as architects, engineers, you need to decide for your system, for the things you care about, your objects, your data structures of interest, should you be using app direct mode, memory mode, or maybe both in some form of hybrid model. So just a quick diversion into what exactly the x10 memory database is. It is a relational database. It has ACID transactions, and you use SQL or PIRL SQL to talk to it. And the entire database is in memory. Because all the data's in memory, it can be very fast. But we're not crazy. We persist the data to files on the file system. And of course, it's highly available. So why did Oracle buy x10? Quite simply, because it was faster than the Oracle database. So we claim x10 is the fastest transactional database, faster than Oracle, the clustered version, the Exadata version, faster than any of these technologies, even faster than these NoSQL type technologies. So that's a bold claim. What evidence do we have? So using x10 with persistent memory in memory mode, we can do a primary key lookup in just over a microsecond. Updates take a bit longer because we need to deal with rollback, redo, undo, if we need to recover the system. So this is not taking NUMA into effect. So this is using 2 sockets, memories wherever. So if we have NUMA control pinning, we can actually make it go faster, slightly under a microsecond. So this was used on this hardware, and I'm going to drill down into this for the rest of the talk. So by the way, this was using 1.4 terabytes of persistent memory. So we're going to go into the details of this. The point is, it can have low latency, and you just write normal SQL select or update statements. If you use multiple connections, you can get more throughput. If you use multiple machines in a clustered configuration, you can get a lot of throughput. So this is running those same 2 SQL statements, 20% updates, 80% reads, ACID transactions. We're getting 153 million ACID transactions per second on 64 machines. So this benchmark's about 3 years old. Technology's got better, faster CPUs. If we reran this with the latest CPUs, we'd probably go a bunch faster. So that's using ACID transactions with updates. So we're still persisting things to disk. So that redo undo was slowing us down. If we just do 100% reads with the same 64 machines, we're able to do 1.4 billion SQL selects per second. So that's primary key lookups. So that's fairly fast for a relational database. How does that compare to NoSQL databases? So there's a lot of them out there. Most of them use some form of clustering. So many years ago, Yahoo was using various NoSQL technologies, and they wanted to know, how do we compare them? So they came up with a benchmark, YCSB, or Yahoo Cloud Serving Benchmark. The point being, you can pretty much use any technology for it. It's doing simple, reads and writes, gets and puts, and it's all about throughput. So you want to maximize the throughput. You can use clusters, you can use as many nodes as you want. Obviously, there's no point using lots of nodes if your system doesn't scale. So if you look at what's the best throughput, it was x10. So we only needed 1 node to go faster than those clusters. So x10 isn't a NoSQL database, it's a SQL database. So we implemented NoSQL get put benchmark using SQL, selects and updates under the covers. So the important thing to remember is throughput. So these are published numbers by the vendors. 1.6 million was the fastest. So we only needed 1 node to go faster. If we use multiple nodes, it scaled more. So we were getting 38 million operations per second on this benchmark with 32 nodes. We only do ACID transactions. So we were doing 38 million ACID transactions per second. The NoSQL systems were doing eventual consistency, which is a fancy word for a random number generator. So in this case, we were using the scale out or clustered version of the x10 in-memory database. So it's a single database with many instances, and it's shared nothing. So how do you program it? You use your favorite language and use the SQL API for that. We just use the Oracle drivers. And it'll pretty much run anywhere. It'll run on bare metal, it'll run on VMs, it'll run on containers. Pick your favorite operating system. Now it does SQL. Just some example here. We're doing a write out of join. We're doing a roll up, so it can do cubes. So you can do transactional stuff and analytic stuff. Here's just another example. This is a single select statement. We've got a with we've got an inner join, we've got partition by. So you can do non-trivial SQL. You know, we support the ANSI SQL, and obviously we support the Oracle syntax. So that was just a little bit off what is the x10 in-memory database. So back in 2008, when Intel had been talking about Optane persistent memory for years, but it wasn't really available. So we were lucky enough to get pre-alpha access to this technology. And we wanted to demonstrate this technology at a conference, our yearly conference. So we had a deadline that we couldn't move. So we had less than 2 months to get something working. So we created some goals. So with x10 being in a memory database, using lots of data, we need lots of memory. So we'd been doing multi-terabyte in-memory databases for over 10 years at that point. But in the past, we had to use basically supercomputers to do that, be it from SGI or HP or Sun or IBM. So they were big, expensive systems. We wanted to see if we could do multi-terabyte databases on cost-effective two-socket machines. So we wanted to, that was our first goal. Our next goal was we wanted to be able to load the database from disk, from files in the file system into memory as fast as possible, specifically significantly faster than we could with the latest and greatest NVMe storage devices. Also, we wanted to be able to do synchronous writes significantly faster than the best NVMe storage devices. Now, because we had less than 2 months, we need to take certain shortcuts, and there are consequences of that, which you'll see. So those were the goals we had. Surprise, we actually met those goals. So on a 3 machine with 3 terabytes of memory, we're able to create a 2.75 terabyte database. We were able to load that database from the file system into memory in 44 milliseconds. So that doesn't sound very impressive, but in reality, that was using a Java program to start up and then attached to that persistent memory. So if we didn't see it, went a bunch faster. The point is, the 44 milliseconds isn't the interesting thing is. The interesting thing is, if we'd loaded it from the fastest NVMe device, it would have taken longer. So this was 2018. Today, those technologies are faster. But in reality, the fastest NVMe disk to do sustained reads, you're lucky if you're getting 3 gigabytes per second. So if you do the math, divide 3 terabytes by 3 gigabytes per second, it's going to take many minutes. So going from many minutes down to 44 milliseconds was significant. For the synchronous writes, we were doing 1.1 million database writes per second. Now, these are ACID transactions. These aren't simple do a write of a few bytes. There's a whole lot of undo, redo type information, so they're quite expensive operations. The net effect was it was 6 times faster than we could do it with NVMe. So that was good. We had to minimize the code changes because we had a very limited amount of time. So if you had a disk-based database that was used to using, spinning disk or SSD, or if you're lucky, NVMe, all of these results would have been amazing. A whole bunch faster, we're done. Problem solved. But it's a bit more complicated than that. We weren't starting from the point of a disk-based database. We were starting from the point of an in-memory database. So that the bar was higher. Some of the things we had to do, x10 was the first commercial in-memory database literally over 20 years ago. Because it runs on all the, popular Unix systems, Solaris, HP, AX, whatever. 20 years ago, we made a design decision to use System 5 shared memory. To use app direct mode, we needed to convert that to use memory map files. In the past, we'd loaded the data from files to the file system, so we needed to change that code so we could just reattach to the persistent memory. Likewise, if we're doing synchronous writes to NVMe, we needed to change that code to do it to persistent memory. So you know, this is very high level of what we did, but the point was it worked, but it wasn't perfect. In app direct mode, you need to explicitly write to the DRAM or write to the persistent memory. The compromises we made to get something working in 2 months was we took all of our data structures and we threw them in PMem. So that made it simple, but the cost was it was slow. So instead of just dealing with transient data structure and DRAM and the more, you know, things that you want to be persistent and persistent memory, we threw everything to persistent memory. So it worked, you know, it was still fast, but because persistent memory's latency is significantly higher than DRAM, you know, it depends obviously, we were seeing up to 3x slower because we made, you know, was it a bad design decision, or if you got less than 2 months, you cut the corners where you can. So the point was we used a suboptimal design to get it working. So obviously since then, we've been doing the engineering work to make the better engineering design choices. And not only that, we also want to have backwards compatibility. So starting from scratch is one thing, but if you want to have a persistent memory at direct mode plus have backwards compatibility, it's a far higher engineering problem. So that's still a work in progress. So that was our experience so far with that direct mode. So I just want to transition now to using memory mode. Instead of doing hard engineering choices, what if we did nothing? So according to the Intel marketing, if you take your system, whatever it is, you're probably going to have hot data and cold data. Now, Intel's got this clever memory controller thing, which is supposed to figure out maybe the hot data should go in DRAM, and maybe the colder data should go in persistent memory. So that sounds good, but the question is, how true is that? How well does it work? So we do know from customer experience that pick any database system, some data tends to be hotter than other data. How much data is hot depends. So I'm talking about the hot data. I'm loosely referring to that as the working set size. So I wanted to try this out. So we got some arbitrary hardware. I'm in California. So SUPERMICRO is just down the road. So we got, this machine had, you know, 2 Intel CPUs. More importantly, it had lots of DIMM slots to put persistent memory in. So if we drill down on that, you know, this was the model. So we arbitrarily chose some SUPERMICRO servers to do some testing. This was the CPUs. So we bought a bunch of them. I got access to 2 of them, one with Linux 7.8, one with 8.2, because we wanted to do a certification process and also see if there was any optimizations in the Linux kernel, latest Linux kernel, which could help us. So we explicitly chose to have a 1:4 ratio of DRAM to persistent memory. So this is a, you know, it's a cost thing, depending on the hardware, you know, the motherboard, you know, do you want to have 1:4 or 1:8 or 1:16? Those are choices. We chose to go to 1:4. So 1.5 terabytes of persistent memory, 384 gigabytes of DRAM. So one of the things I learned is, you know, there's some system admins set up the system. Don't trust what the system admins people say. Check what's actually configured. So I'm using IMCTL to show what we've got there. So in this case, app direct mode isn't being used. It's all in memory mode. So for a lot of the testing I was doing, I wanted to compare app direct mode versus memory mode. So I do a lot of stuff of setting a goal, doing a reboot. Don't know about you, I always get a bit nervous when you reboot. Will it come up? The point being, there were 12 slots for PMem because we're using 128 gig DIMMs. That gave us 1.5 terabytes of memory, and we're using 32 gig DRAM DDR4. So we've got a one-to-one relationship between DRAM to PMem. You know, if you're into hardware, this is a 222 configuration. And obviously we could have chosen to have 256 or 512 modules to have larger capacity. So that was a choice. So we got some hardware. Now we need a workload. You know, there's an infinite number of workloads. I wanted to choose the simplest possible workload which still had customer relevance. So, you know, there's been a lot of things published about Optane P memory. Most of those things published, I consider to be micro benchmarks. They, you know, they're easy to do. They're very good at picking out a specific thing. You know, they're minimizing the variables. But I wanted to, you know, elevate the problem. Let's look at what real customers do. So this is admittedly a very simple problem, but this came from a customer. So this is literally metadata about VPN users for virtual private networks. So the point is, we got some tables. I added this padding column for some testing. We'll cover that later. But more importantly, I inserted a bunch of rows to populate 1.4 terabyte of data with this padding that turned out to be just over 160 million rows. What's the workload? We're doing some lookups and some updates or writes. So we're doing primary key lookups and we're doing updates based on the primary key with a commit. So these are ACID transactions. So this may be a fairly simple workload, but fairly simple but really fast, low latency, high throughput workloads is how our customers tend to use times 10. If they, you know, if they don't need to go that fast, they have a lot of choices with databases. If they need to do stuff in microseconds, that's quite often where our customers come from. So the workload TPTPM, don't ask me what it stands for. It was a customer workload. So I'm particularly using it, I'm using it in C via ODBC, and the way I was testing it was multi-process, doing a fork and exec. You can do it multi-threaded. You know, I've been doing pthreads for 20 years. My conclusion is single process is easy to code. So if you look at it, I mean, this is just a screenshot up top. Because it's multi-process, each process has got its own PID. We can see from the virtual memory used, that's approximately 1.4 terabytes of data. If you've written your code well, if it's optimal code, for an in-memory database, you should be using 100% CPU for each core. Why? Because you shouldn't be waiting for disk I/O, you shouldn't be waiting for network, you should be going as fast as possible. If you write your database sufficiently and you code, you know, your client code efficiently, you should be minimizing system calls, you know, context switches, because they just slow you down. On this machine, because there was 2 sockets, lots of CPUs, I still had, you know, a bunch of idle CPU, and, you know, there was some CPU wait, and there was a little bit of swapping going on. So if you're using memory mode, you got to ask yourself, how much persistent memory is really being used? Because it's not actually obvious. From our experience with at direct mode, if you exclusively use persistent memory, it can be a lot slower. But when you're using memory mode, the way Intel's configured it, you're always going to use some DRAM as a cache for the persistent memory to make it go faster. So one way of looking at it is, if your working set is smaller than your DRAM size and you have a predictable workload, PMem is probably not being used. I say probably because it's not obvious. If your working set size is so large that you're using all of the persistent memory, you're not actually using all of the persistent memory. There's still some caching going on. So it's going to be proportional, and that's going to depend on the ratio of DRAM to PMem. So what I was particularly interested in was to see how the working set size affected performance. By performance, I mean latency and throughput. Now, I'm a firm believer, I mean, you can do tests, you look at the inputs and you look at the outputs, but I'm an engineer, I want to know what's happening. So I'm looking at the CPU hardware events to figure out what I think was happening is actually what was happening. So this is my new favorite toy. So this is an open source technology, process counter monitor. So it's looking at those hardware events. It's a Go program, it's making the system call. So that's a little Prometheus exporter, and Grafana every now and then polls it. So what it allows you to do is look at interesting metrics, things like how many persistent memory reads and writes versus DRAM reads and writes are occurring per socket. You can see things like, excuse me, how utilized are the UPI channels. So that you can look at it over time and you can correlate events. So this is just a screenshot. There's many pages off this. So instead of writing this all myself, I found this incredibly helpful to figure out cause and effect. I had my theories of what was happening. Here I could check what actually was happening. Now, back to my benchmark. So I've got a single table called VPM users. It's a table, so it's got rows and columns. So you can think of it as an array of structs if you're a C programmer. So I wanted to use all of the persistent memory. So I created a table of 1.5 terabytes, and that worked, but I couldn't figure out why it was going slow. I dug down a bit, it was swapping because I forgot the Linux kernel and the file system buffer cache needs some memory. Likewise, all my C programs. So I arbitrarily made it smaller, 1.4 terabytes. It all worked, it stopped swapping. So I don't know how big, would it work to 1.45 terabytes? I don't know, I haven't tested that. I just made it smaller to get the tests out quickly. So maybe if I made it smaller, it might go faster. I don't know, I wasn't focused on that. The point being, with 1.4 terabytes of data, I filled it up completely with data, rows in that table. So that was it taking up effectively 93% of my PMem because I had to leave this extra overhead for the Linux in my programs. So given my table width, that was taking up about 160 million rows. So what I was particularly interested in was how does the cache hit ratio, how does the working set size affect the cache hit ratio? So if we look at the worst case, if I accessed all of the rows from the first row to the 160 millionth row with equal probability, my working set is basically all of PMem. So that would be worst case. In that worst case, the DRAM cache hit ratio should be approximately 25% because I've got a 1:4 ratio. So that's worst case. So even in worst case, I'm going to get some DRAM caching, which is nice because it's faster. If I used a smaller working set, if I artificially constrained the workload, say between 40 million and 60 million, say only deal with 20 million rows, because that is sufficiently small that theoretically could all fit in DRAM, the theory is I should have a higher DRAM cache hit ratio and things should go faster. So that was my theory. So I wanted to do some tests. So how do you artificially constrain it? I looked at using different distributions. So if I did a uniform distribution using DRAM 48 as the pseudo-random number generator, I could vary A and B to come up with the working set size. So if A was 0 and B was the maximum number of rows, my working set would be all of PMem. If I move A and B, I can artificially make the working set smaller. So that's easy to do programmatically. So I also did a bunch of tests with various Zipfian and Poisson distributions just to see how things affected it. So these are not customer workloads. These are simulations of customer workloads. So I did a bunch of those tests. The results I'm about to show you only used the uniform distribution, and I state what the bounds are. Is it all of it or is it some fraction? Just one thing with the benchmark approach. This benchmark we've been using for over 20 years, so we understand it very well. I did my tests with 10 million, 100 million, and 1 billion iterations because I wanted to have very predictable response times, very stable answers. So 10 million to 100 million or 1 billion, you'll pretty much get the same results. If you use less iterations, there's larger variance. Because of the operations I'm doing, you know, they're less than 256 bytes for the selects or updates. So those, because the data is so small, it can fit within a cache line. So, you know, am I hitting L1, L2, L3 cache? Am I hitting DRAM? Those are all unknowns. So because it's small, you can get caching effects. So I was doing many iterations to give stable results. So that's good in one case, but it also hid some of the results that I was going to see. So it's sort of a two-edged sword. So the first thing I wanted to do was see, I wanted to get a baseline. I had 384 gigs of RAM. I artificially constrained my workload to fit within half of the DRAM. So if my working set should theoretically be guaranteed to work within DRAM, I was hoping I would get a good high cache hit ratio so that my tests using memory mode, I could then compare to app direct mode when I was only accessing DRAM. So it turned out my results matched what the Intel marketing said. The Intel marketing said for memory mode, it should be the same. And based on my tests, it was. So I'm doing 100% reads. So if I'm using 48 connections, that's giving me just over 20 million SQL selects per second. So I'm getting fairly linear scaling. There's a bit of a dip here, I'm not quite sure why. So I was getting the same throughput with memory mode as I was in app direct mode when I guaranteed that the working set should fit within DRAM. So that was a good result. My machine had 48 cores. I did the test, it actually scaled all the way up to 96, but when you get into hyperthreads, it dropped off. Because with hyperthread, you know, you're sharing, when there was no waiting for disk I/O or networking, so the rate dropped off a bit. So I didn't do this test once. I did variations of these tests over and over for, you know, over a week to get predictable results. So the point was, the baseline, if your working set is going to fit within DRAM, that was a good result. I repeated the same thing for writes. So, you know, there was a 20% write workload using 36 connections. I was getting a bit over 2.5 million transactions per second on this one machine. So that was a good result. So if your workload fits within DRAM, it goes just as fast as if you were using DRAM alone. So what I had want to see was the relationship between the cache hit ratio and the working set. So the worst case is the working set was using all of PMem. The best case was, you know, I was only using 1,000 rows out of 160 million. There was actually very little variation. You know, this is, you know, 1.1 microseconds. The worst case is, you know, about 1.7 microseconds. So that's a bit of a confusing result, but I believe it's an artifact of the way I was testing. I'm doing this 10 million times. So I've effectively have a warm cache. So you could argue that's not a valid test, but I would argue it's in a memory database. You want to have the data in memory all the time. This is actually how customers use the product. They want a warm cache. So it made it hard to see the effect, but I believe this is the mode that our customers actually use the product. So if you have a very predictable workload and you run it with enough iterations, say 10 million, I was getting very little variation in latency. So it wasn't what I expected, but it was a good result. Likewise for the writes, a bit over 4 microseconds to a bit over 5 microseconds. So even if I'm using all of PMem virtually versus, you know, only 1,000 rows, pretty consistent latency. Once again, this is an artifact of the way I'm testing. Now, this is what I really wanted to test. Instead of constraining the data to just DRAM, I made sure that I was accessing all of PMem. So I was using my random number generator. So I may be hitting, you know, hundreds, you know, I'm doing an even distribution of all the rows in the table, which means I'm accessing up to 1.4 terabytes. So my effective working set size is 1.4 terabytes. So the interesting thing is I still got linear scalability. So with 48 connections, I'm still getting just over 20 million transactions per second. So I'm getting the same performance using PMem, using all of PMem, as I was when I was just using DRAM. Why? Because the DRAM caching effect and the fact that I've already warmed up the cache. So this to me is a very good result. I wasn't expecting results this good, but I was very happy with that result. So I got good scalability and I actually got the same throughput as I did before, even though my working set was substantially larger. For the writes, same sort of deal. I was still getting just over 2.5 million transactions per second. You can't really see it in the graphs. There was a bit of a drop off. The writes didn't scale quite as well, but it was still pretty good. So because I was using a warm cache, it's a bit hard to interpret the results. This is my interpretation. If I'm using a working set that should fit within DRAM, using Intel Optane memory mode for both reads and writes, I was pretty much getting the same results as if I was using DRAM only. So reads, I basically couldn't notice the difference. Writes weren't quite as good, but at worst they were 5% less throughput. So I thought that was a pretty good result. When I was forcing the working set to use all of PMem, because of the way I was testing, the cache hit ratio didn't really make that much difference to the throughput. Like I said, I didn't expect this. I was expecting bad results, but I was quite happy with the outcome. Likewise, when I'm forcing all of the P memory to be used, persistent memory, the read and write scalability wasn't really affected that much. Read, I basically couldn't tell. The write scalability was minimally affected. So so if I compare that to the prior work done with micro benchmarks, this is actually a pretty good result. So the conclusions that I draw is that the way I was testing wasn't perfect, but I believe the way I'm testing is how my customers actually use the product with warm caches. So because I had fat rows, I could only fit 160 million rows in the 1.4 terabytes. I repeated the exercise with much thinner rows, with 2 billion rows, and I got the same results. So the width of the row doesn't seem to affect it, which seems very counterproductive. But the way I did that was with a padding row. That padding column. That padding column wasn't selected or updated. So even though it was taking up space in memory, it wasn't, you know, once I put that row into the CPU, the padding wasn't affecting the cache line because the actual columns, the number of bytes used was less than 256 bytes. So padding to make it fewer rows or more rows didn't really affect the result. So that was one conclusion that I draw. The second conclusion was, I really wanted to know how good this memory mode was if you have predictable workloads. I didn't know how good it was going to be. I had no expectations. For this workload, on this hardware, it was incredibly efficient and effective. So I don't know how efficient or effective it will be for different workloads with different hardware. We need to do those tests. But for these particular tests, it gave very good results. So what that means for me as a developer and product manager is we've certified memory mode so that you can use the x10 in-memory database. The good thing is, for the sort of workloads that we expect customers to use, it gives low latency and high throughput without us having to change any code, which is a good outcome. So I think that covers everything I wanted to cover. So we've got about 15 minutes of time, so I'm very happy to answer questions.
Great, thank you, Doug. There's a couple questions coming through on the chat. So one was, I'm curious as to how much longer latency it was to how a slightly longer latency to PMem would affect the performance of x10.
Great. So we do have the information for that. If we exclusively use persistent memory when we use app direct mode, it's slow. You know, it's up to 3x slower. So we wanted to use persistent mode because it sounded like a cool thing. We made bad decisions because we had to rush it through in 2 months. So if we exclusively used persistent memory via app direct mode, the latency is 3x slower, which obviously hurts the throughput. So that's a data point. So like I said, we are re-architecting the product to be smarter about that, to only use persistent memory when we need and use DRAM elsewhere. In parallel with that, we were doing the certification for memory mode, and it turned out by using memory mode, if we have very predictable workloads and a large DRAM cache-hit ratio, the latency and throughput was minimally affected. So I wasn't expecting good results, but we got very good performance via PMem in memory mode. So hopefully that answered the question.
Yeah, I had a follow-up to that. I was wondering if you had any intuition about why you didn't see a bigger negative effect. Like, is it just that the database is built to be tolerant of memory latencies already, and so that engineering paid off, or are the accesses to PMem just not on the critical path? What's the do you know why?
Great question. I spent a week asking myself that question. I'd like to say my product's perfect and that was the reason. I don't think that's the case at all. I think it's an artifact of how I did the measurements. If I measured every single operation, do get time of day, I would see variance and that would give me data points. What I was doing was, I had a warm-up and I was running the tests for millions of operations. So I believe the caching warm-up effect meant that the working set, the rows of interest were probably already in DRAM. So I think that effect skewed the results to make the latency be minimally affected. We know it's impossible for the latency not to be affected, but because we have a 1:4 ratio of DRAM to PMem, and I'd done a warm-up, I believe those two factors, plus the fact that I did, at least 10 million iterations, hid the latency.
Great. A couple of people are asking about how x10 manages persistence. Are you using the persistent memory for persistence, or is it going out to SSDs? And related to that, how does logging work?
Great questions. So, two answers. The product today out of the box uses files on the file system. You can do synchronous writes to the files and they will be slow. You can also do asynchronous writes. If you take the writes out of the code path, it doesn't really matter how slow your disk is. You just have to have big log buffers. Obviously, we have multiple machines for high availability because you don't want to have a single point of failure. So the product as it is today, most of the time we do asynchronous writes to make things go fast. Obviously, using SSDs or preferably NVMe devices gives you far better performance. So that is the product as it is today. When I use the product as it is today with no configuration, no code changes in memory mode, using asynchronous writes, and it'll just work nice. So that's one answer. If you're using in memory mode, we still persist to files on the file system, and it works very nicely. The prototype we did back in 2018, so like we know what not to do. We're re-engineering it to use persistent memory. And do we still need files even if we've got persistent memory? That's one of the design decisions that we're still noodling over.
Great. Would it make sense, assuming it was possible, to use DRAM explicitly for things you know are hot, like logs and indices, and memory mode for the rest?
That sounds like a great idea to me. So, I mean, at a high level, yes, we have many data structures, many moving parts. The details really matter. It's an ongoing engineering process, and I'm just going to give that high level answer. Yes, it sounds like a good idea. Details, when we release the product, we can tell you more. So just to be clear, the product's been available for 20 years. Using it in memory mode is available now, it's certified. We're working on a version which more explicitly uses app direct mode.
All right. The performance of x10 is impressive. One thing that wasn't clear from your slides, loading 2.75 terabytes in 44 milliseconds. How many servers or how many PMem devices are you loading from?
Great question. That was a single 2-socket machine. We're not really loading it from disk into memory. That's impossible. We had used app direct mode to create the database. So we had persisted 2.75 terabytes of data into persistent memory. So that's the prerequisite, the precondition. If we shut down the database and then start up the database, all we need to do is, start up some daemons and reattach to that shared memory. To that persistent memory via it happened to be a Java program because we had a graphical user interface on it. That attachment time was what took 44 milliseconds.
Did you monitor DRAM miss rate by chance on memory mode in your study on large size data sets experiment?
Absolutely. If you don't look at those hardware events, the DRAM hits and misses in the PMem local and remotes, you're guessing. You literally don't know what's going on. So I used the hardware events, I like that Grafana process monitor thing, so I could see cause and effect. I firmly believe that unless you see what's actually happening, you have no clue. So Intel, in my opinion, has done a very good job. It's magic, but when you use the hardware events, you can see what's really going on.
All right. Have you done testing with random accesses to data that fills up the PMem and is all used rather than just ignoring the data or some of the data?
So if I understand the question, I believe that is what one of the tests was doing. One of the tests forced the working set to use all of persistent memory. So I was accessing all 1.4 terabytes. I was doing random access for both reads and writes. So that's the worst case. I was doing that test. Because I was warming up and because I was doing at least 10 million operations, I was getting very good latency and very good throughput. So if I understand the question, I believe that is what one of the tests was.
All right. So someone asks, with app direct mode, is x10 really an in-memory database running out of DRAM?
Great question. So we did a prototype in 2018, and for that prototype, all of the data structure, everything we put in persistent memory using app direct mode. So that's a prototype. We're re-architecting the product to make it more efficient than that. Whether you call it in a memory database or not, that's more subjective. That's what we did.
I was curious about the engineering process you go through to figure out what to put in PMem and what to keep in DRAM. Can you talk any more about how you're deciding what goes where?
That's the $64,000 question. You know, we've got a lot of smart engineers, a bunch of PhDs, and they have, shall we say, active discussions.
All right. Let's see. If I've missed your questions, you could post them again. Some of them are scrolling by pretty quickly. Someone asked, did you try to run the servers with DRAM and PMem in memory mode, but DRAM not as a cache for PMem, but rather to get as much memory as possible? So I guess using the PMem and the DRAM separately without the caching mechanism.
Yes, I did. I may not have made that clear enough. Using the IPM CTL tool, you can set a goal of whether, you know, how much memory mode, you know, is it 100% memory mode, 0% memory mode, or some mix. So I had a lot of tests to do exactly that, to get a baseline. I also compared it over, you know, I had several machines to play with to make sure that the results were stable. I also compared it to machines with, you know, large DRAM machines that had similar processors because I wanted to make sure I was measuring what I thought I was measuring. And the result of all that, comparing the memory mode versus the app direct mode versus machines that had no persistent memory, I was getting consistent results, which also matched the results for the known workload that we've had for the last 20 years. So the answer is yes.
And for the good results that make it appear that the Intel memory manager is great, could it be that the CPU is the actual bottleneck and hence the reduced sensitivity to optimizations?
Maybe. The way I'm testing definitely makes it hard. I think I'm hiding the latency. I know how our product works. It's a very fast product. We have, you know, it's not magic. We have internal latching. At some point you get contention. I believe we're seeing more times 10 internal contention rather than Intel CPU contention. So, I mean, so that's my belief. Looking at all the hardware event counters as a data point to give me more confidence in that answer. Good question. I don't think so.
All right. Well, thank you everyone for those great questions, and thank you again, Doug. You can visualize a big round of applause from the audience.